Hey, so let's get started. We got a lot to do today. So I guess I'll start with the news. So this is a story that most of you have probably heard about, or maybe not. But you might not have thought it was a 61C story. There's been terrible floods in Thailand, especially in the capital city of Bangkok, and it's a terrible. So I need you guys to quiet down. So, it's been a terrible disaster in terms of the human toll. A lot of people have died and a lot of people are left homeless. What you might not have realized, and actually I didn't realize it until my lab started trying to buy a bunch of servers, that it turns out that a huge percentage of the world's disk drives are made in and around Bangkok, Thailand. Okay, so, and in fact, about 25%, according to this article. And all those factories have closed, and so 25% of the world's capacity for making disk drives has just instantly gone away, and that's going to have huge repercussions. So for one thing, it makes PCs and other kinds of servers more difficult to get, and therefore more expensive. And if you think about how that's going to ripple through the whole ecosystem, people are basically going to stop buying PCs, or they're going to buy fewer of them. They're going to buy fewer computers. That means the other components that aren't made around Bangkok, the supply for them is going to be too much. So a lot of the DRAM manufacturers, for example, are worried that the price of DRAM is going to start plummeting. Okay, so I show you this one just because you might think when you hear stories like this on the news that maybe it's not so related to what you're studying. But the fact is, the world is so interconnected now, and the supply chains for the systems that we use are so big, and the impact of the systems that we're building is so big that pretty much anything that happens in the world is going to have some sort of impact, and anything that you do in this area is going to have some impact. And so I just put that out there for you to take a look at that. All right, so what we're going to do today is finish up our discussion on control of the data path. And remember, we've got these 5 steps that we maybe haven't been following in lockstep, but we're going to look at our instruction set. We're going to figure out what the requirements are. We're going to figure out what parts we need for the data path, and then we're going to assemble them. And then what we're going to talk about today is we're going to look at each instruction to figure out what control lines need to be set to make each instruction happen, and then we're going to put together actually the logic to make all that control happen. Because up until now, we've had this view that these control signals kind of magically get set. But as you probably figured out from lecture and from trying to do your own homeworks and projects, there actually isn't really any magic here, unfortunately. And we got to make this all work out of the components we have. And so we're going to have to come up with the logic to actually make the control happen. So we're going to try to get through all of that today. So we're going to focus on these 2 steps. Here's kind of I think something I finished up with last time. I want to go through it once again because it's just super important. So remember, we're building the single cycle CPU. So we're going to go through our whole 5-stage instruction processing series of steps or pipeline in 1 clock cycle. So that's what I'm showing here. From here to there is 1 clock cycle. And so when the clock goes up, we're going to read the PC, the program counter. There's going to be a little delay there, right? That's the clock to queue delay of the register that's holding the program counter. Once that delays happen, we now have a new value, so we know the address of the next instruction that we need to execute. So what do? Well, we go to instruction memory and we fetch it. Okay? That's going to be in level 1 cache, hopefully, so it's going to go quick. It's going to go quicker than a single cycle, but there is some delay. Okay, so there's the delay to read the instruction from the cache. At some point, we get that new value we get the new instruction, and then we start decoding it. And when we decode it, we figure out what it is, and we start trying to make sense of it. So what you can see happening here is there's going to be a delay going through this control logic that we're going to build today, and after that delay, we're going to get new values for our control signals. And this is what happens when we're doing an arithmetic operation, like an add or a subtraction. So that's going to impact 2 control signals. We're going to get a new value for our ALU controller, right? Namely, is it going to be an add or a subtract? And then we're going to get a new value for the register write control. Remember, that's the thing that tells us that at the last step of the instruction, we're going to update the register. All right, and that's going to be set to 1. Okay, so now we've gotten the instruction, we've encoded it, we've decoded it, we've set some control flags, and at the same time, when we look at that instruction, it tells us that there's registers that we're interested in. Okay, and in particular, if it's an add or a subtraction, we're interested in 2 registers, because the ones we're going to add or subtract. And so we've got to go to the register file, which we talked about last time, and get those out. So there's going to be some delay. After that delay, we now have on the bus coming out of the register file the value for register A and the value for register B. Those get sent to the ALU to have the operation that's going to be indicated by this control flag, so an add or a subtract. And then there's some delay for the ALU. At the end of that, a new value pops out. And because we have the register write flag set, when the clock rises the next time, the register that's going to hold the result of this arithmetic operation gets updated, okay? Because that's going to be set to 1, okay? So we went over this last time, but it was quick, so I wanted you to see it again. But any questions on that before I move on? Because we're going to see a few different variants of this. Yeah? I'm sorry? Okay, so where's the memory access time? In this instruction, right? It's an add or a sub. So there is memory access, but it's just to get the instruction. Okay, the instruction itself isn't going to memory. Okay? Yeah.
If there was a situation where the memory access, the instruction memory access time took so long as to
Not finish.
how would the processor?
So we're going to start talking about that next class. So if you go to memory and like for some reason get that instruction you miss in the instruction cache, when might that happen? Anybody? When are you likely to miss in the instruction cache? Yeah, when you do a jump to some place that's far from where you are now. So it does happen. The pipeline's going to stall until the memory returns. So we'll tell you what you're going to do, but for now, just assume that the whole thing just goes idle until the memory comes in, until the memory returns. Okay? All right, cool. So that's really important. Make sure you spend some time staring at that. I know I had to, just to make sure you understand what's going on. But hopefully it'll become a little more clear after we go through the rest of what we're going to go through today. Okay, so we talked about adds and subtracts. I want to talk about a few more of the operations. Remember, we've got this MIPS Lite subset that we're doing that has, half a dozen instructions in it. And so we just did add and subtraction. Another operation in there is OR immediate. So, what does that look like? Well, remember, that's an I-type instruction. So what that means is we've got our 6-bit opcode, we've got 2 registers, and then we've got 16 bits of immediate value. Okay? So if you recall, here's kind of what our main circuit looked like with the register file feeding into the ALU, and then the result of the ALU coming back and being fed back into the register file on this bus W, the write bus. Okay? In order to do OR immediate, there's 2 things that have changed, okay, and I've highlighted those in red. One thing you'll notice is we have to get the immediate bits, okay, so there's going to be 16 bits, but we've got a 32-bit ALU, so we've got to turn that into a 32-bit quantity. So we've got this box here called a 0 extender, okay, and what that's going to do is just pre-pen 16 bits worth of zeros on it. So the thing that's going to pop out on this 32-bit, so we've got 16 bits coming in, we've got 32 bits coming out, and the 32 bits that come out look like this. What was in these 16 bits of the instruction, prepended with 16 zeros in front of it. Okay? So that's going to come out of here. Now, remember in our previous example, in our previous diagram, bus B was going right to the ALU. Okay? But now we've got a choice, okay? Because in this case, we're not reading anything from bus B. In fact, what we want to go into the ALU is the register that's on bus A, right? Because what we're going to do is we're going to OR, we're going to OR this register with this immediate value, right? And we're going to write the value into RT. So the first thing we're going to do is we've got to put a multiplexer here, right? When we have to choose between multiple signals, we put in a mux, and that mux is going to have a control signal, okay? And this control signal, you have to sort of forgot that you knew vowels. That's ALU, well, there's one vowel in there, but that's the ALU source. So basically, if it's a 0, then this input, the second input of the ALU, is going to be from bus B. If it's set to 1, then it's going to be this 0 extended immediate value. Okay? So we've now got a new control signal that we have to set. Okay? Okay, now there's something else going on here, which is in the R-style instructions, we were writing to the destination register, RD, right? In the I-style instructions, we don't have that third register, so what we're going to write into is RT, right? That this register that's identified by these 5 bits here. So we need another switch, right? So our muxes are going to be our, the railroad switches, right? That tells us, directs the signals where they need to go. So we need another switch here that basically, and that's the registered destination. And basically, that's going to feed into the write line of the register file, right? Because we have to identify which register is going to be written. And we've got a choice. If this thing is set to 0, then it'll be RT, like it is in this instruction. If it's set to 1, then the register that'll be written will be RD, as it is in an R-style instruction. Okay? So we've put in yet another switch. Okay? Now, there's another thing here that you might worry about, which is, wait a minute, I'm still pumping RT. Not only am I sending whatever is in RT into this mux here, okay? I'm also sending it into bus B. Okay, so there's actually an RT read happening here. Okay, but do I have to do anything about that? Do I care about that? Are we okay with it? Yeah, we're going to be okay with it because we've got this roadblock here. This thing, it's a traffic cop. It says, okay, whatever's on bus B, you're not going any further. Whatever came in on this line, that's what's going to the ALU. So even though, Dan, when he first introduced these kinds of circuits, talked about the fact that everything was all happening at the same time. So there are bits flowing through this RB input, but it doesn't matter, okay, because they're going to get blocked here. And again, that's going to happen because we're going to get our control bits set at 0 or 1 at the right time. Okay, any questions about this? So it's very similar. All of these are going to look really similar, and it's just a question of how many data switches do you have, and how do you set those control bits. So it's pretty amazing, actually. Okay, good. You guys are better at this than I am then. Okay, couple more types of instructions. Luckily, it's a small set, and we're halfway through. So let's talk about load operation. So what are we going to do in a load operation? Well, the new complication for load is that now, instead of just dealing with registers and immediate values like we were doing in the previous kinds of instructions, we've also got to deal with memory, okay? And that's where the extra complications come in. So let's see what's new here. Okay, so what we're going to do in this load word, we're basically going to take the value that's in register S, we're going to add that to this 16-bit immediate, right, those 16 bits of the instruction, and that's going to be the address that we want to load from. We're going to go to memory, we're going to take that address, and we're going to get what's there out of memory, and we're going to write that into register T. So again, we're updating register T here. So if you look at the extra plumbing we put in here, this looks similar to what we had last time, right? It's an extender, except it's doing a different kind of extension. Okay? So this one was a 0 extender because no matter what you give it, it just puts 16 bits of zeros in front. Okay? But here, we have to do sign extension, right? Because that offset might be negative. So it's a slightly different type of extender. So what we're going to do is we're going to build one extender, and we're going to have another control signal, this extender operation, that goes in here. And if it's, I forget whether it's 0 or 1, but if it's set one way, it does 0 extension, hopefully 0. And if it's set to 1, it does sign extension. Okay? So that's a new control signal. The other thing is now we've got memory. So we take our address that we got. We take our immediate, I'll lose my voice here. We take the immediate value, we sign extend it, we put that in the ALU, and what do we do with it? Okay, well, we add it to whatever the value in RS is. So RS comes in on bus A, this assign extended immediate comes into the ALU on the second input. And we set the ALU control to say, hey, add those together. Because that's what the instruction needs to do, right? It's going to take the address that you get by taking what's in RS and adding the assign extended immediate value to it. Okay, so we actually use the same ALU that we use for our arithmetic operations to do the addition here to come up with the right address. Okay, does everyone see that? Once we get that address, we present it to the memory, and the memory does a lookup. The memory, think of it as a big array. That address is an index into that array. A word comes out of this memory, and then we've got to do something with it, right? What are we going to do with it? Well, we're going to write it into a register. We're going to write it into the register identified by RT. All right? So the problem is, if you look at our previous circuit, we had a direct line going from the ALU back to the write line of the register file, right? But you don't want to do that here because what's coming out of the ALU isn't what you want to write. It's the address that you want of where you're going to do the memory lookup. Okay, so it's a different thing. So again, we need another data switch here that says, hey, you know what? For this instruction, I don't want to write what's coming to the ALU back into the register file. I'm going to send, that's going to the address. What I want to do is I want to take the thing that's coming out of the memory and write that back to the register file. Okay? So we've got another control signal, right? Another mux and another control signal. This one's called mem to reg. If it's set to 0, that means we're not sending the memory to the register, which means the ALU is going to go. If it's set to 1, that means whatever comes out of the memory gets put onto bus 0. I'm sorry, bus W. Okay? And, by the way, we have a control signal that we've seen before, which tells us whether we're going to take what's on bus W and write it into the register identified by RW. Okay? And so if reg write is set to 1, we're going to do the update. If it's set to 0, we'll just ignore it. Is that a stretch or a question? Or both? Look like both. Yeah?
From the look of it, everything that comes out of the ALU goes both to the data memory and to the sequencer. Because the result of every arithmetic operation we do gets treated sort of as an address, and we just decide whether or not we want to have that address.
Okay, that's a really good question, and one actually I hadn't thought of when I looked at this. So the question is, the way this picture is drawn, it looks like everything that comes out of the ALU gets sent to the memory for a lookup. And do you really want to do that, given that most of the stuff that's coming out of the ALU isn't addresses? And I think this picture is inaccurate in that regard. I think, you know, we're not going to activate the memory unless we really want to read something from it. Okay? Because otherwise, memory is too expensive and too slow. So really, thank you for pointing that out. Yeah? Does this, okay, good, another good question. Does this happen in one clock cycle? Absolutely. Okay, except, oh, sorry. If it doesn't, okay, I'm sorry. Remember, this memory is sort of an abstract box. If you remember, what's in there is level 1, level 2, level 3, right? And then finally DRAM. And if the data we're looking for, if we've got good locality, then the data we're looking for will be in level 1 cache, and this will return in time. If the data we're looking for isn't in level 1 cache, we very well likely won't return in time, and that's going to be a memory stall. And that's what we're going to talk about, again, starting next time. Yeah?
What about the part where it flips from like into memory or into the multiplexer mem to reg? Would that be then like a defector or something?
I don't actually know how that's implemented, so I don't want to make something up. Yeah? Yep.
I was wondering, why did they make it so that you, like, sometimes like the RD is so that you guys want, why not make it so that you always, if you're writing to it, you always have
Okay, so that's an interesting question. So why when we created our MIPS instruction, by the way, Dan, you should listen to this because you're going to answer this question. So when we created the, so the question is, when we created the MIPS instruction set, why did we do it such that sometimes the second register is where we write and sometimes it's where we read from? Why not just always make the second register the thing that gets written?
here. It turns out if you look at all of the RTL for all of the I-types and the R-type guys, that it actually doesn't matter whether you do the flop where you always write to the second guy or not in terms of the number of muxes you need and the signals you need to set. It actually doesn't matter, so they chose it that way to sometimes write to one, sometimes write to the other. So it's I can look up to get the more specific thing, but it turns out you'll see that it doesn't actually matter.
All right, so that's okay. And, you know, this makes it more confusing, so it makes your degrees more valuable. That also helps. Okay, any other questions that I can get Dan to answer? Or I can answer. All right, cool. All right, so we've got a couple more. We've got now, we loaded things from memory into registers. We got to go back, right? We've got stuff that we've computed that we want to write out to memory. So same format of the instruction, a lot of the same stuff. We're doing the same address calculation where we sign extend the immediate. We add that to the value that's coming in on bus A, and that tells us where we're writing. But now we need a couple other things. We need a switch or control signal that tells us that we're going to write memory. Okay. We still have our address coming in from the ALU, but we've got one other problem, which is we've got to get the data that we're going to write. Okay, so we've got to write data into memory, and the question is, where's that data going to come from? Not looking at your slides. So I've got this wire that's just sitting there. What am I going to hook that up to? Looking at this instruction. Okay, so what are we doing? We're taking what's in RT, what's in the register, what's in register RT, and we're going to write that into the memory location that we get based on the base that's in RS plus adding the offset. So where's this data in going to come from? It's going to come from RT, which where's RT coming? It's RT is going to go fed into RB. That's going to come out on bus B. So we've got to have another wire here. Okay? So if that animation was too quick for you, here there's a data in. We've got to wire that up to bus B. Okay? So this all makes sense, right? It's all logical. That's why it's called logic. Or I'm not sure that's why it's called logic, but it should be. So that's how we do a store. And you can see that, you know, kind of for each of these different types of operations, we've got a control signal or a set of control signals that we need to set that's going to make the same hardware do the right thing. So rather than have a separate, you know, you could imagine, you know, I've got an instruction set that's got, you know, a couple hundred instructions. Maybe I could build a separate circuit for each one of those. That's not what we do. Okay, we've got this main processor that's doing, you know, the bulk of the instructions, at least, you know, at least the integer ones. Okay, and we're just setting these switches to the right way to make the right instruction happen. Okay, I'm going to talk about one more instruction. There's actually two in the book. I'm going to talk about branches, and the book also talks about jumps, and you should look at that. But just in the interest of all of our sanity, I'm not going to spend any time on jumps today. But you can look at it and see how it would work. It's a good way to test your knowledge. And on the slides that I'm about to post on the website, there'll be some slides on jump, but I don't have them here. So, but branches are the remaining one that's in our MIPS Lite set. And the way branch happens is, so what are we going to do? We're going to do a branch on equal. So we're going to test whether RS and RT are equal. Okay. If they're not, the branch, we're going to fall through the branch and just go through, we're just going to go to the next instruction. So we're going to increment the PC by 4. If they are equal, then remember the branch is going to be an offset. So we've got this immediate value. That's the number of words after or before the next instruction that we're going to jump to. Okay? So we're going to sign extend that, and we're going to add it to the next instruction, and that's going to be our the address of the next instruction, that's going to be our PC. Okay? So we got to do that equality test of those two register values, right? The things that are in those registers. If they're equal, we're going to jump to this new instruction. If they're not equal, we're just going to fall through to the next instruction. So what that means, the way that really gets implemented is, guess what? we're going to have some special logic in front of this PC register that's going to decide, right, is that the value that goes into the PC, or is that the value that goes into the PC? And we're going to have to key that off of the equality. Okay? So let's see what that looks like. And this is a place where I want to apologize a little bit, which is the slides, in order to keep them simple, you know, there's one thing that's not shown very well. I'm going to show it better in the next slide. But again, the things that are different are what I'm showing here. And there's one important thing over in our main loop, which is this equal bit. Okay? Or if you look in the book, it's actually called the 0 bit. Okay? So why is it called the 0 bit? We talked about this when we looked at the RTL, right, to describe the branch on equal. The reason it's called the 0 bit is because we're going to subtract RT from RS, right, the value that's at RT and the value from that's RS. And if they're 0, right, if we subtract one from the other and the result is 0, that means they were the same. Okay? So we get to do a comparison in our ALU for free. We don't need any new logic. All we need to do is make sure that the ALU control bit flags are set to do subtraction. We're going to pump in the value from RS and the value from RT. We'll do the subtraction, and we've got this special flag coming out of the ALU that's going to set to 1 if the result is 0. So it's called the 0 bit, or 0 flag. But we're going to, just for sanity here, I labeled it equal. Okay, so in the book it says 0. Here it says equal. Just remember why that is. Okay? So we've got this equal flag coming out. But remember so that's how we decide which way we're going to go. Okay? But now we also have to do the arithmetic to figure out, to get to the right address. So, you know, we have two choices. We have the choice we take if those things are equal. Okay? And we have the choice that we take if they're not equal. So, not surprisingly, we've got a new multiplexer here. Okay? And we've got two things going into the multiplexer. One is the result. So the PC is a register. We're going to take the value of the PC, which is the current value of the PC. We're going to have something that's always 4, and we're going to add 4 to the PC. So that's going to be our branch. If we end up falling through this BEQ, that's the address of the next instruction. That's the thing we've always done with the PC. We just have an adder that adds 4 to the current PC. Okay? The other path, though, that's the path where we're going to actually take the branch. What do we need to do there? Well, we've got to sign extend the immediate value. And remember, this is only in all this stuff here is in the instruction calculation logic. So it's not in this main loop that we're talking about. So here, we don't need one of these, you know, all-purpose Swiss Army knife extenders. We just need an extender that does the right thing for an address. So we'll call that the PC extender. And basically, that's just going to sign extend this immediate 16-bit value. Okay, and we're going to add to that the value of, right, the address of the next instruction, because that's the way we define BEQ, right? It's an offset. I'm sorry, this thing also, if you remember, is shifting the thing 2 bits, because we want to translate from words to bytes. So this extender shifts it to the left 2 positions and does sign extension. Okay? And then we're going to add that to the value, to the address of the next instruction. And then what we need is some logic for deciding which way to go. Okay? So we've got a new flag here, a new control flag, which is the impossible to pronounce NPC cell. I'm not sure I remember why the N is there. Okay? So this, what's that? Next. Oh, thank you. See, this is why we pay Dan the big bucks. N stands for next. Okay, thank you. Why isn't it capitalized? Okay. All right. Well, all right. That's why he's not going to get a raise this year. But okay. So, but just setting that flag by itself, 0, 1, isn't going to do it for us, right? Because why? Well, because there's really 2 things that have to happen here. Okay? So, you know, how are we going to decide which path which path are we going to take? Okay, and the answer is there's really two things we have to worry about. Okay, one is we need to worry about is this an operation where we might take this extra address, right? Because most addresses, most instructions, we always take the +4, right? We always just go to the next one. Okay, so this NPC cell, the next PC selector, if it's 0, that says always just go to the next instruction. Okay, if it's 1, then that means, hey, this is a branch instruction. We might we have to make a decision here. We might go one way, we might go the other. So if that's 1, then we look at this equal bit or the 0 bit, and basically, oh, well, okay, this is better if it says equal. If they're not equal, so if equal is set to 0, then that means that means the branch, we're going to fall through the branch. That means the equality failed, and we're going to go to the next instruction. So the result should be 0. On the other hand, if we did that subtraction and the result was 0, so this is a 1, you got to kind of flip this on your head a little bit. So we did the subtraction, the answer was 0, so that means the 0 flag or the equal flag was set to 1. That means we are going to take the branch. That means we want this input, which is the 1 input. Okay? So here's our logic table. We've got to fill that box in. So we've got a box now that takes the NPC selector and the equal bit, okay, or the 0 bit, all right, and outputs a 0 or a 1 according to this truth table. So what goes in that box? And this is not meant to be a hard question. What do you want to put in that box? AND gate, yeah. So you guys, I insulted your intelligence, I'm sorry. Yes, an AND gate. Yeah, so that's what goes in there. So this NPC selector is a little different because it's got to take, 0, 1 tells you, 0 says, I'm always just going to the next instruction, I don't care what happens. Okay, 1 says, hey, I'm actually doing a branch operation, so I do care what happens. So 1 says, if for the branch on equal, says if they're not equal, okay, fine, fall through the branch, just go to the next instruction. If they were equal, then I do want to follow the branch, and then I take things from this path. Okay, so it's all, yeah, go ahead. I'm sorry? Why are there 2 zeros on top of PC? This is, why are there 2 zeros on top of the PC there? Because we're always, because I guess what this is showing, so I did steal this from a different slide deck, so maybe there's an slight assumption of where this is happening. But remember, addresses always have to be on word boundaries, so the 2 zeros are indicating that the first 2 bits of that thing have to be a 0. I'm sorry? Yeah, I think that's right. And so I'm not sure I like having those 2 zeros there. That's what I get for adding slides at the last minute. But the point is that, the way I showed it to you before on the previous slide, this PC extender was adding the two bits. And, was doing the shift of 2 bits. And we're always, the way we talk about it, we're always sending in 32 bits. We're always adding 4 to it. Okay? So, yeah. Go ahead. Either one. Yes. Okay, so the comment is, boy, it seems that when you have to mess with the PC, that makes things more complicated than just adding a new instruction. So if you're adding a new decision instruction, like a new kind of a branch or like a jump, it makes things more complicated because you have to mess with this logic here in addition to the main logic. And you are right, and that's one reason I'm not showing jump here, because to make, think about this logic, right, this instruction fetch logic, when we have yet another option. Right now we only have 2 options. Go to the next instruction or branch. But we also have these things called jumps, which say, no matter what, go to this immediate address. Okay? You got to think, right now this circuit doesn't handle jumps. And so if you want to do a jump, you got to extend this circuit to make it do that. Is that your comment too? Or, yeah. I can if it doesn't take too long. No, well, we subtract bus B from the value that's in B from the value that's in A, and this flag gets set. If that result is 0, then a 1 pops out of here. Exactly. This is the property of, this is, don't do any more work than you have to. Not that we're encouraging you to think that way, but we are actually, because we're trying to do engineering here. So yeah, it's like we already have the circuit that can do the equality, so why implement something different? Yeah.
Will there be a case then where messing with the PC will take longer than messing with the ALU and everything else, or will that use the ALUs and all that usually take longer?
Okay, so the question is, will there be a case where all this stuff takes longer than the ALU? And the answer is, well, certainly, anytime you go to memory, there's a risk that that's going to take a long time. Okay, this processing here, you do have to design your processor carefully to make sure. One thing that we talked about a little bit last class, and we'll talk about, I hope, again a little bit in another class, which is you have to figure out this critical path through the circuit. And so you have to figure out, even when things are happening in parallel, you're going to have to take the longest path, the longest possible path from here all the way around, and that's the speed that your clock can tick at in this single cycle regime that we have. Okay? Wow, more questions. Yeah? Do I need another control to implement? Branch not equal? Good question. Do I need another control to implement branch not equal? I probably do, yeah. I probably need another mux or an inverter or something. Yeah, I suppose we would. So that goes back to the comment earlier, which is, whenever if you're doing different things to the PC here, you have to, it's a little more complex maybe than just changing another, just a regular instruction. But, to go from branch equal to branch not equal, it's really just an inverter. But there is going to have to be a signal that says, use that inverter or don't use that inverter. Yeah, it's a conditional inverter. Yeah, we actually already know how to do that. Right, thank you. But it is another signal that has to trigger that conditional inverter. One other question? Yeah. I'm sorry? Yeah, the NPC select is going to be dependent on the opcode. Where does it come from? That's awesome. That's what we're going to talk about next. Is right now we're assuming that these signals sort of get magically set. This equal is kind of the first one where we saw where it gets set. It gets set in the ALU and it gets wired back, connect that wire back there. We haven't actually talked about how the other stuff gets set, and that's what I want to talk about next. So let me keep moving. Okay, good. So now let's actually start talking about that exact question. So here's a picture that kind of ties everything we've talked about so far together. It's got all the control signals. It's got all the muxes. The other thing that it's showing that we hadn't seen before is this little picture of what's coming out of the instruction memory. So remember, instructions are 32 bits, right, in the MIPS architecture. All the instructions are 32 bits. And basically, when the instruction, the address comes out of the PC, that tells us to read the instruction at that address. Okay? A 32-bit word will come out of the memory, and what we're going to do is we're going to parse it this way. We're going to take bits 0 through 15. We're going to put them on this immediate 16 line. We're going to take bits 11 through 15. That's our 31. That's a number 0 through 31 that tells us what our register D is. Bits 16 through 20 tell us what register T is, and bits 21 through 25 tell us what register S is. And then remember, we have an opcode. Oh, well, this is for an immediate one. But the other bits are the opcode, right? We have a 6-bit opcode. Okay? So that's how we're going to start to set those control signals, is because we're going to look at the opcode bits and the function bits, and we're going to have logic that translates those bits into turning on and off the right control signals. So this is what that's going to look like, right? So here are all control signals and the different options they can be. So for example, this register destination, right, where we decide which register is the one we're going to update. A 0 tells us it's register RT, a 1 tells us it's register RD. So we've been through all those before. I put them there for just so you remember. But this is really the picture that you were looking for. We're going to take the instruction that comes out of memory, and we're going to pump these bits into this control logic, and out of that control logic is going to be all our control signals, right, that then go into the data path in those places that we showed on those diagrams, okay? So now all we have left to talk about, oops, I missed that one. All we have to talk about now is how we're going to do that translation. How are we going to go from the opcode and the function to these control bits? Okay, so if you were ever not going to talk during a lecture, now is the time, okay, for you guys talking? Okay, so good. So here we go. So because we don't have much time for this, I'm going to have to hold off on questions for a second. So here's an add instruction. It's an R-type instruction, so we know what it looks like. And so we're going to get 6 bits of opcode, we're going to get a bunch of other stuff, and we're going to get 6 bits of function. Okay, because remember, for arithmetic instructions, opcode is going to be 0, and the function bits are going to tell us what instruction it's going to be. So here's our fetch unit, nothing fancy here. We take our result from the PC, that gives us an instruction. We get 32 bits out. And then here's what we're going to do is we're going to take the opcode and the function codes, and that's going to turn on and off a bunch of different signals. So that's going to say ALU control is add, mem to register is 0 because we're taking it from the ALU. We're not writing anything to memory. You come back this way. We're going to write register D, so this is set to 1. We are going to actually do the write, so that flag is set to 1. Down here, we're not doing any extension because there's no immediate. There are bits coming in on this immediate bit bus, but we're not going to look at them because the ALU source is set to 0. That means it's going to come out of the second input to the ALU is coming out of bus B. Okay, so by looking at that, the opcode and the function for an add, that's going to set all these flags to the right thing, and the right thing's going to happen. That's what we're aiming for. Okay, so sorry, I was going to walk you through it this way. I forgot I was going to do that, but actually, it's probably worth just a second. So we're going to read the add. So again, the input's coming from bus B, which means it's not coming. We don't care what we do with the immediate bits because they're going to be ignored. They're going to get blocked at that mux. The operation we're doing is an add because we're going to know that by looking at the opcode and the function code. Adds don't write memory. They don't write anything from memory into a register, so those are both set to 0. They do update a register, and the register they update is the destination register, RD. Right? So if you remember, we had this register, this RTL language, right? The register transfer language. That's exactly what it told us. It told us all those things. And so we just have to encode that into circuitry. And then, the next instruction is going to come. It's just the next instruction. We're going to add 4 to the PC. So we're going to set this NP select flag that we just talked about. It says +4 here, but +4 means we're not doing a branch. Just go to the next one. Okay? And then, so that's what it looks like at the end. So if you look in the book, and this really starts to answer your question, the instruction, comes into this control, and this control sets all these flags. And so I don't want to walk through this picture. I just wanted you to see it. It's in the book. It's picture 4.17. I added it after I printed out your handout, so it's not there. But it's in the book, and I wanted you to see it because that kind of shows you for the first time that this control isn't something magic and something that's kind of sitting outside the box. It's actually part of the circuitry. Okay, and it's going to be driven by the bits that make up our opcodes and function codes. So here's our. We looked at this before. This is our register transfer language. Okay, and this says, for example, that an add basically takes what's in register RT, adds it to what's in register S, writes the result into register RD, and then increments the PC to the next instruction. And so that means these are all the way the flags have to be set. For subtraction, they're all the same except that the ALU control is set to sub instead of add. Okay? And then you can read through these and see how each of those instructions gets implemented in RTL. So now this is really it. This is logic. This is kind of the big slide. This is the logic table for the controller. It's the truth table for the controller. Okay? So basically what it's saying is, let me stand over here because it's a little bit of an eye chart. Here's our opcodes, and it's 0, 0, or one of these other opcodes. All right, if it's 0, 0, we also care about the function. 1 with a bunch of zeros is an add. 1, 0, 0, 0, 1, 0 is a subtraction. Okay? Otherwise, we don't care about the function. We just look at the opcode. So if we see opcode 0, we have to also look at the function to tell us which ALU function it's going to be. Otherwise, if it's another opcode, the function doesn't matter. And then for each of these, you can just read down this. So for an add, register dest is set to 1, register write is set to 1. We don't care about the extender. Ignore jumps for now. And ALU controller has to have more than 1 bit. So we've got subtract, we've got add, we've got or. So that's going to be 2 bits actually. Okay? But there's going to be bits that come out of this. For sub, it's the same except for the ALU control. Right? For or immediate, we're not writing anything. Reg dest. Sorry, we're writing to register T. That's what 0 means. The ALU source is a subtract, right? Oh, well, anyway, I'm not going to mess it up for you. You get the idea. But each one of these. X means you don't care, and again, don't worry about jump for now. Okay? So basically, that's just a big truth table, and not surprisingly, because it's a truth table, you can write Boolean logic, Boolean algebra to describe it. So the reg dest flag, if you look at that, is the operator an add or a sub? Okay. If it is, then you set it to 1. If it's not, you set it to 0. The ALU source, if it's or immediate or load word or store word, then you set it to 1. Otherwise, it's set to 0. Okay, and you can just read this thing down. Memory to register. So we're going to write from memory to the register. For all instructions, it's 0, except if the instruction is a load word. So if load word is 1, then we set that to 1. Okay? And you can just read that down there. And then, basically, we can now, so this, these are basically variables that tell us the names of the instructions. And then here, we talk about how we do the Boolean algebra to compute which instruction we have. So we want to know, is our instruction an R-type? Okay. Well, what's an R-type instruction? Well, an R-type instruction, we know the opcode is all zeros. So basically, it's opcodes. These are the 6 bits of the opcode, and we basically take the and of the nots of them, right? So it's not so 0 is not 1, 1 is not 1, and 2 is not 1, and 3 is not 1, right? So if they're all zeros, then our type is true, okay? ORI has this expression, and LW, right? And these are just the bits of the opcodes, okay? Now, we have a special case for R-type instructions, which is if it's an R-type instruction, then we also have to look at the function bits. So that's what this is saying. If R-type is true, and function 5-bit is true, and the 4th bit of function is 0, and the 3rd bit of function is 0, and the 2nd bit of function is 0, and so on, then it's an add. If it's R-type is true, and this is all the same except that this bit is set, then it's a subtraction. Okay? So this is where it happens. We've now we've taken our instruction set from the register transfer language into Boolean algebra, and now we've got it down to the points where we're actually looking at the bits of the instruction. We're ANDing them down here, we're ORing them up here, and that's what's setting our flags. So this ends up being a circuit that looks just like that. This box takes the opcode and the function, and it does this stuff down here. So we know out of that AND box, we get whether we're doing an add, a subtraction, an or immediate, or so on. Okay? So we know what instruction's coming out, and then those bits get put into the OR logic, and those OR logic sets these flags according to this algebra right here. Okay? So now all we have to do is build up this controller logic here with a bunch of AND gates, take in these inputs with a bunch of OR gates, and out pops all the control signals that we've just learned about. Okay? And those control signals are going to be sufficient to do our entire subset of MIPS Lite, right? All 6 of those instructions. Okay? So here's where I'm going to stop today. I want you to think about how you add jump, and if you look online, I'll have the slides for jump. It's also in the book. I'll revisit this again on Friday, and then we'll move on to the next topic, which is how to do this stuff in parallel. Okay?